now let's move to the session 8, cloud and the user space system. I'm Zheng from USDC. And in this session, we have 4 papers here. So now let's welcome the first speaker. Okay. So the team from the first paper is emailed me due to some reasons which not attend personally, right? So they just dedicate you are the Enge Wang, right? Yeah. So to present the paper. Okay, so I will just quickly introduce Enge Wang. Okay. So Enge Wang is a master student at the University of Chinese Academy of Science and is currently an intern at Alibaba. His research interests include cloud networking, EPCs, and high-performance networking for AI systems. Okay, so without further ado, this slide.
Yeah, thank you. Hello, everyone. This is Enge Wang from Alibaba Cloud. Today, I will present our work titled Single Core Hotspots on your VNF. Break them up. This work studies a practical performance issue in cloud network functions. Single core hotspots caused by elephant flows and presents parallel a vSwitch assisted architecture that enables per flow parallelism while preserving packet order. Network function virtualization has become a fundamental technology in modern cloud infrastructure. Cloud providers deploy many virtualized network functions, such as load balancer, net gateways, and firewalls, on general-purpose CPUs inside virtual machines. Although modern VNFs run on multi-core architectures, most of them still follow a flow affinity execution model. That is, packets belonging to the same session or flow are consistently steered to a single CPU core within a VNF instance. This design choice is mainly driven by 2 considerations. First, it avoids packets out of order. If packets from the same flow are processed by multiple cores, the system needs synchronization or software-based reordering, which consumes significant CPU cycles. Second, it avoids shared state contention. Since many VNFs maintain per flow or per session state, concurrent accesses from multiple cores may introduce synchronization overhead. However, this design has a downside. When traffic is scaled, especially with elephant flows, one core can become overloaded while other cores remain underutilized. This creates single core hotspots. This problem is not only theoretical. We observe frequent single core hotspots in Alibaba Cloud's VNF deployment. In our example, a fast-pass instance had 5 cores, where 1 core was reserved for control tasks and 4 cores handled data plane processing. During an elephant flow event, 1 processing core reached around 50% utilization, while the other 3 remained below 15%. Since the system raises alerts when CPU utilization exceeds a certain threshold, which is 40% in this case, this event immediately triggered internal actions. To understand the broader impact, we analyze system-wide alert logs over 1 week. Single core hotspot alert accounted for about 46% of top 2 severity incidents and occurred more than 2,500 times. These frequent events introduce operational overhead and affect service quality. Several mechanisms have been proposed to address intra-server load imbalance. First, static methods such as ISS distribute flow across CPU cores using hash-based mappings. However, they are unaware of runtime traffic dynamics. When elephant flows appear, a single core can still become overloaded. Dynamic solutions such as Xingku and its ISS introduce runtime scheduling mechanisms to redistribute flows or tasks. These approaches can reach to workload changes, but they mainly rely on migration. Migration can move a flow between cores, but it cannot overcome the fundamental limitations of per-core processing capacity. Where a small number of elephant flows dominate the traffic, the bottleneck still remains on one CPU core. Another direction is to deregulate parallelized packets from the same flow. For example, Spire distributes packets across multiple cores to achieve higher parallelism. However, packet-level parallelism naturally introduces packet reordering, which can affect application-level queues and limits practical deployment. Therefore, existing approaches cannot simultaneously provide dynamic balancing, true per-flow parallelism, and strong packet order guarantees. Based on these observations, we propose PowerFlow. The key idea is to break elephant flow into smaller processing units, parallelize them across multiple CPU cores, and restore packet order before delivery. PowerFlow introduces two key modules inside the vSwitch: a breakup module at ingress and a reorder module at egress. At ingress, the breakup module detects elephant flows and split them into flowlets based on time intervals. It then dispatches these flowlets across different CPU cores. Specifically, for flow with PowerFlow enabled, the vSwitch assigns a reorder queues and a packet sequence number. This metadata allows the system to reconstruct packet order later. To enable per-flow parallelism, PowerFlow uses a flowlet-inspired traffic scattering mechanism. Instead of assigning a flow permanently to one core, PowerFlow periodically switches the target core of the flow. Each flow remains assigned to one IX queue for a fixed interval and then moves to the next queue. This creates coarse-grained flowlet-like units without requiring explicit inter-packet gap detection. The switching interval is dynamically adjusted according to processing delay. Therefore, PowerFlow can distribute load across cores while avoiding excessive concurrency on the same flow. At egress, PowerFlow restores packet ordering through a lightweight reordering mechanism. After packets are processed by different CPU cores, the vSwitch uses the reorder queue ID and packet sequence number to place packets into the correct position. Once packets arrive in order or when a timeout occurs, the packet is released through the normal switching pipeline. To reduce memory overhead, PowerFlow supports metadata-only caching. Instead of storing complete packets in the vSwitch, it only stores packet metadata and fetches the full packet when needed. We perform a preliminary evaluation to validate two design choices. First, whether reordering becomes a bottleneck. Second, whether PowerFlow can balance CPU utilization and eliminate hotspots. First, we evaluate whether packet reordering becomes a bottleneck. On Smartnik RISC-V cores, reordering achieves about 4 million packets per second per core. For comparison, production network functions such as firewalls and net gateway typically process around 1 million packets per second per core. Therefore, although reordering introduces overhead, it is still several times faster than typical NF workloads. With multiple RISC-V cores, the aggregate throughput can exceed 400 gigabits per second for large packets. These results indicate that SmartNIC-based reordering is unlikely to become the system bottleneck. We also evaluate whether PowerFlow can mitigate single-core hotspots. We simulate a 4-core system with one elephant flow and multiple small flows. Under ISS, the elephant flow is pinned to a single core. As a result, one core reaches around 80% utilization, while other cores remain around 10%. In contrast, PowerFlow distributes the elephant flow across multiple cores. All cores achieve approximately 30% utilization. This demonstrates that PowerFlow can eliminate single-core hotspots without requiring VNF modification. In summary, current VNF systems rely on flow affinity to preserve packet ordering and avoid state contention, but this creates single-core hotspots under scaled traffic. PowerFlow addresses the problem by enabling per-flow parallelism through V-switch assisted flow breakup and lightweight packet reordering. Our preliminary evaluation shows that reordering is not the bottleneck. PowerFlow can effectively balance CPU utilization, and metadata-only cache significantly reduce memory overhead. That's all. Thank you.
Okay, thanks for the great talk. Let's speaker. Okay. Okay. Is there any questions from the audience? Okay. I have a question. How are elephant flows packaged, and how does the system handle the misclassification? I hope you can solve my problems. Thank you.
Okay, thank you. Elephant flow detection is not the main contribution of this paper. PowerFlow can consume text from upstream telemetry system or use local indicators such as byte rate and packet rate. Selecting the best detector and threshold is part of our future work, and now we are mainly on the PowerFlow itself, not the elephant flow detection. Thank you. Okay.